Welcome to the online causal inference seminar. Today we have Iavor from LinkedIn talk about causal inference challenges in industry, a perspective from experience at LinkedIn. We're very excited about this talk and looking forward to it. Afterward, we have a discussion by Iavor from Harvard Business School. Iavor is also in Q&A, so please submit your questions there. He'll try to answer them. Yeah, that's it from my side. I'm now switching over to Guillaume.
Thank you, Dominic. So as usual, the questions will be handled through the Q&A. So as Dominic mentioned, Iavor will be, who worked with Iavor a while back and is familiar with some of those ideas, will be manning the Q&A today. We will also select questions to ask to Iavor directly during the talk. So again, please submit them through the Q&A. If your question is selected, I will reach out to you via the chat and ask you to raise your hand so I can identify you, and then I will unmute you. So yes, please do not raise your hand unless I've asked you to do so. Thank you very much. That's all from me. Iavor, you may start whenever you are ready.
Great, thank you. Let me actually start sharing my screen. Good morning, everyone. Hope you all had a wonderful Memorial Day long weekend, at least for those of you who are in the US. So I am super excited to sharing some of the things that's related to causal inference that we do at LinkedIn. First, just a very high level intro about myself. Sorry, that's my kid in his Zoom meetings classes as well. So I got my math and economics degree from Williams College, and then went on and got my PhD in statistics from Stanford. Worked at Microsoft Bing for 3 years, and now I've been at LinkedIn for 7 years and counting. Really, most of my time are spent in industry in the space very closely related to causal inference. So I'm gonna divide up my talk into really 3 sections today. I'm gonna introduce a little background, really about both about LinkedIn, because I think some of the examples I've been sharing will be very relevant to how LinkedIn is operating, and also just some general background on how causal inference or experimentation as well is done in the industry. And now I'm going to go into challenges, 4 challenges that we face in particular, and then I'm going to go to the applications, talking about a few applications that I think are quite interesting. So for those of you who are looking for really deep statistical theories, that's not what we're going to cover today. Our focus today, my intention today, is really introducing some of the challenges to this group so that I can get more people interested in solving this problem with us, or solving this problem so we can leverage your solutions. So with that, I'm gonna get started. First section on background. So for those of you who are not familiar with LinkedIn, LinkedIn is really, our vision is to create economic opportunity for every member of the global workforce. And the way we think about LinkedIn as the professional social network is that obviously we have lots of nodes on the graph. The nodes really are the entities on the what we call economic graph, which is a digital representation of the global workforce that has members, close to 700 million members, and we have millions of companies, jobs, skills, and schools all on this network, on this graph, interacting with each other. So now that's just kind of like a very high level brief introduction of LinkedIn, but thinking about going to the topic that we're going to be discussing today, causal inference really is riding on the very much top of the pyramid when it comes to hierarchy of evidence. And then if you're thinking about, as we or any company that is trying to evolve either their product or their sales or the go-to-market motion, it's super duper important for all of us to understand the cause and effect, right? And so today I'm going to be primarily focusing on the two components of this pyramid, which is really the randomized control experiments and also the observational causal studies as well. So primary focus will be on controlled experiments, but I also touch upon some natural experiments, non-randomized observational causal studies. So coming back to LinkedIn again, that's relevant to causal inference. And really the question is, we do a lot of A/B tests, and here is just giving you a simple example of what we A/B test on. So certainly if you can see pretty much every single component in the app, all the way from the search box to new feature that we're launching, to the ranking algorithms, to the reaction buttons, to navigation, to ads, to comments, like every single piece of what you see on the phone, on your phone, on the app, or on the web page, or any changes that we do to that, we actually A/B test on them. And that's not just yet, right? So if you're thinking about that, what you saw was just on the very much the surface of literally sort of the tip of the iceberg. And in order to support our app, there is a humongous amount of infrastructure that goes behind it as well, from the network to offline infrastructure, online infrastructure, data centers, everything that's there. We actually experiment things that's not just going into what people are able to see, but all these things that's invisible to our members as well. So just to give a sense of in industry how people are using A/B testing to improve their product, their experiences over time. This is a simple example where it really shows that Bing ads over time is using A/B tests to improve inch by inch. That is really able to increase their product experience, their monetization over time. And LinkedIn, along with Bing, Google, pretty much in the past years since these companies have started to A/B test, that we have seen over 10 times of growth within the first 5 years of them starting to experiment or building their experimentation platform and being able to experiment very heavily. And those three companies now pretty much all are experimenting at about 20,000 experiments a year, which is really a lot, considering the number of experiments that's running. So just wanted to, again, I'm not gonna go into very technical detail. I will give a lot of references at the end of my talk if you're interested in to read upon more of those in detail. But just kind of like mentioning a little bit of like how in those tech companies that we are able to allow for that many experiments running is really this overlapping architecture where we essentially are making randomization of users into each of the buckets, but are we using essentially a different hash ID that we use for different layers and for different kind of experiments that we're running. So in this example, you see here, we have an ads layer that is essentially dividing up the users into 5 different buckets for treatment, 1 control. And we have a different search layer that is using a different hash ID that is splitting users into treatment and control that is orthogonal to the ads layer. So that essentially is the high level background. And I'm gonna pause for a minute to see if there are any questions. And if not, I can continue to the second section.
No, there are no questions at the moment. I think everything is crystal clear.
Okay, great. Okay, so I'm gonna go over 4 challenges. In particular, like I mentioned, I'm not gonna go in depth on how those challenges are like solved technically. But my goal primarily is to introduce those problems and give you some sense of the way that we are solving them at LinkedIn in particular. I would love to maybe stimulate some creativity innovations among this group because all these challenges that I'm gonna be mentioning today are not solved, right? So we have some solutions that is able to help address some of those challenges, but they are not even nearly close to be solved at all. So the 4 challenges, the first one is really the leakage and interference in controlled experiments. So let me actually kind of start by going back to this, I would assume pretty well-known assumption among this group, which is really this assumption that a lot of times when, especially folks in industry who runs a lot of A/B tests and whatnot, like we kind of forget that this is actually a very important assumption. It's this SUDVA, right? So stable unit treatment value assumption. What it really is saying, as a reminder, is that each individual's response is affected only by their own treatment assignments, right? It's not depending on how the others' treatment assignments are. So the reality is that we actually see a lot of use cases where you cannot assume this anymore, right? So this, each individual's response is actually affected by other people's treatment assignments. So if I'm kind of categorizing, again, this is what we call interference, also known as leakage or spillover. If I kind of categorize this at a high level, I want to say 2 categories of interference. One is really when 2 nodes or 2 entities, or in this randomization unit, right? 2 units, they are directly connected with each other. And then there is another category is that they are not directed, they don't seem to be connected with each other at all, but because they actually using shared resources and there's sort of a latent variable that is really underlying the connection between those two units. So I'm gonna go into a little bit more depth by means of some examples. So the first example is really the social network example on this direct connection category of interference. So this is now imagine that you are on LinkedIn, that you have everyone has a lot of connections, right? So they're all connected with, people are connected with each other. So let's say I actually have a treatment that is really encouraging people to send more messages, right? So some of you actually, for those of you who use LinkedIn, sometimes you actually see a little prop or see a notification say, hey, it's your best friend or who, your colleague's birthday. So why don't you send them a happy birthday note? So that is, let's say that's my treatment. That is really encouraging James in this example to send more messages to Morgan. And then the thing is that Morgan, who is in control, will end up sending more messages too. Right? Because if I get a message saying happy birthday, it's courtesy for me to then respond and then say something back. And then again, they could actually rekindle some of the older connections that people have. And then again, they can start to engage and chat with each other more. So now you can see why that is problematic, right? Because I had a treatment that is encouraging James to send more messages. And that is not supposed to be affect people in control. However, Megan, who are in control, end up sending more messages as well. That is what that interference started to be problematic for our A/B test. So we have really been working on this problem for quite a long time. I'll share some of the solutions that we have tried in the past, and I'll talk a little bit also about what their pros and cons are. So the first solution is really what we call cluster-based randomization. So compared to the Bernoulli randomization, which is really you take a user in this case, right? And then what we call members. You take a member, you flip a coin for each of the members and decide, hey, should this member be in treatment or should this member be in control, right? So represented by the red and the green dot. But instead of doing that, we're gonna take the graph the social network graph, the LinkedIn graph, and we're gonna cluster the members on them first based on the connections, right? So the rule is really about you wanted to cut as many edges as possible between clusters. You want to contain as many edges as possible within the cluster. And then once you have clustered the graph, then you can go and assign treatment and control label for the entire cluster at a time, right? So the entire cluster are either labeled red or labeled green. So we had done that. Our very first paper was essentially doing the cluster, and then when we go ahead and analyzing them, right? So when we analyzing them, we have a model-based approach, which is really sort of like thinking about the size of the network effect, depending on the network exposure that people have, and the problem, and then again, I welcome you to go ahead and read the paper. It was besides many technical challenges of clustering a really big graph and how you can go about cutting as little edges as possible between the clusters, the biggest challenge that we faced, especially for applications in industry, is that we realized that because this is a model-based approach, the estimates of both the network effects and also the final effect varies a lot depending on the model you choose. You can have various different exposure models, and then the answer will be very different. And it's really a no-go for people working in industry, because you're like, wait a minute, like, what do you mean by the estimate is 1 today and then 3 tomorrow, depending on the model you choose. So that's sort of the first approach. It was a very interesting scientific study. But I want to say not quite practical for us to use. So the second approach that we did was less about let me sort of measure the overall impact. We actually started this by a very simple question, which is, hey, can we just we always talk about network effect, and it's seems pretty intuitive that there should be network effect, but can we actually detect it scientifically, right? So what we did is essentially we did a randomized over randomized experiment. Basically, we take the entire graph, right? We break it into 2, and half of the graph is going to get Bernoulli randomization, and we're going to measure treatment effects based on that, right? Which again is going to be biased if there's a sizable network effect. And then the other half, what we did is we actually then clustered it, which is exactly the methodology that I mentioned earlier, is just cluster, and then we randomize based on the cluster, right? So then we're gonna measure what is the difference, the treatment effects difference that we measured based on the first Bernoulli randomization, and then based on the cluster randomization, and then see, hey, is there a significant difference between these 2 approach of how we randomize to see is there actually a real network effect. And then obviously the result was very positive, that especially not every interactions or feature or changes that we saw had a significant that we were able to detect the delta between delta. But we certainly saw for big changes that we also anticipate having network effects certainly showed up very prominently. So the problem of this approach, and actually similar with earlier approach, is really that in practice, because the network is so dense, I want to say, and the way that people cluster with each other, it's extremely challenging to have good isolation. As a matter of fact, we actually tried a lot of innovative ways to cut the graph. Then what ended up happening is that we still are seeing there are 80% of edges actually between clusters, right? So which really means if there is let's say my network effect size is 10, I'm only able to isolate 2. Right now, the 8 points is gonna still be cut, or is still gonna be interfering between different clusters. So not very good isolation. And the second limitation is really about low power, right? So if you're thinking about, we have millions of users members that comes and visit LinkedIn every day. But once you started to do a cluster, you can only do, I believe that the time we did maybe what, like 5,000, 1,000, like, so that essentially is your sample size. So very small number of clusters relative to the number of users. So very low power. So then we started to look into a different approach. Again, a very successful study that proved that in practice that there are strong network effects in some applications that we have, but not very practical to use for us in practice. So we started looking at this ego-centric experimental design, which is really that in the cluster-based approach, once I cluster the graph right into the little clusters, every nodes in the cluster are treated equally, right? They are either all getting treatment or all getting control. But this one is a little different. So what we're gonna do is we're actually going to be treating the center node, what we call ego, to be different from the ones that's on the outside, which is the alters, right? So if I wanted to see what is a network effect, I'm gonna take a control ego cluster and give everybody control, including the center node, and I'm gonna give I'm gonna take the treatment ego cluster and give all the alters the treatment, and but the center node control, right? So if I compare the center nodes from control ego cluster to the treatment ego cluster, the only thing that's different is how their friends are treated, right? So that is really allow us to be able to measure that network effect a lot more effectively, and which is really something that we actually use quite extensively in our production system. So coming to the third solution, which is what I call age-based analysis. So this is really try to take advantage of that some leakage actually happens with a very clearly defined interaction. And the example that I used at the beginning, which is the messaging, right? Messaging is happening very clearly defined ages and interaction. So now imagine that, this is really just a picture of, you have people in control, you have people in treatment, and obviously treatment can talk to control, control can talk to treatment, and vice versa. So I can really label all the ages, and depending on the treatment assignment, to these 4 categories, right? So treatment to treatment, treatment control, control to control, or control to treatment. And with that setup, and I can actually, if I can measure everything properly, I can actually measure what the true delta is by really just comparing the treatment to treatment connections and control to control connections, and then the delta in between. Not only that, again, thinking about this messaging example, we also wanted to be able to measure this, what we call response rate difference. So if you imagine that a treatment is encouraging me to send more messages, but the message, depending on the kind of messages that I'm encouraged to send, that extra message may actually have a higher or lower response rate to the individuals I'm sending the messages to, right? So we also wanted to be able to measure what that response rate difference is between treatment and control. So I'm not gonna go into details, but basically we actually have to construct again, I wanna say a simple model that is extremely realistic, right? So really what we are modeling is to say, hey, there is a decay effect, right? If I send you a message and there is the probability of you respond back to me is alpha, and then the probability that I responded back to your message, then it's obviously lower, right? So there's a decay effect that we're modeling. But other than that, it's a super realistic model, and we'll see that in the data as well. So with that, we actually are able to measure what we consider the true delta is based on the messages that we saw between connections. That is either between the messages between treatments and the messages between control, and also the response rate as well. And the key here is really that there are some assumptions that we're making here. In particular, something that I actually didn't quite mention earlier is what we call affinity, right? So is treatment more likely to send messages to other people who are also in treatment versus other people who are in control, right? So that if that is if that matters, then we say that there is a treatment affinity. If that doesn't matter, then we say there's no affinity. So basically, this measurement only works if you actually do not have affinity. But one thing again, we are able to test for affinity and actually measure it. So one thing that we are able to see in this real data, first of all, is that you can see that there is the simple delta that we measured through the traditional A/B test, and that is quite different from the true delta that we measured. And in some cases, that is like not too different, but in some cases you can actually see it's over 100% difference between the simple delta is 100% biased. So again, we also are able to measure response rate. Different experiments actually have quite different response rate, which is really interesting, right? Because one thing that you wanted to, when you are designing a feature, is you wanted them people to continue that conversation versus, hey, it's one conversation and then people just ended up not talking to each other afterwards. So the one thing that actually is really exciting for us, again, the earlier this measurement actually takes, it's very expensive to compute. It's an assumption that's very hard to estimate. One thing that we were able to prove was actually there is approximations that you can do that basically just take a simple the simple delta for sends and receives, and then you add them together, and then that is able to actually give you a lot of the good estimates, assuming that there's no affinity. The one thing I want to say is that what we also have found is and proved is that if the experiment actually has equal traffic allocated to treatment and control, so if you do a 50-50 experiment, then these are true as well. So super exciting for this, because then it really allows us to be able to scale this method to all the hundreds of experiments that we run in parallel every day. And we also are able to validate it. So as you can see this, right, so we have the corrected lift and we have the approximation of the lift. The x-axis is the lift that is really through this computational expensive method. And the y-axis is through the approximation. And as you can see, when there is even split between treatment and control, which is the darker blue, they are pretty much right on the line, right? So very good approximation. Okay, so I'm gonna go a little quicker because I feel like I'm probably running out of time. So the second example category is this indirect connections, and I'm gonna use the budget constraint in ads as an example. So just so that folks are familiar with this, so if you imagine like Facebook or Google or LinkedIn, we also have our ads as well. So advertisers wanted to like show ads to users, right? So what they do is they say, hey, this is my budget. I wanted to be able to spend $1,000 with LinkedIn, and LinkedIn, you figure out how you can like show who you want to show to, and then like try to spend that $1,000 while achieving their goals of reaching to the customers. So now you imagine that this $1,000 and I created an ads campaign that is already 100% budget utilized. So that essentially means that we're already really good at spending that $1,000 for the advertiser and achieving their goals, right? So now you imagine that you have a treatment that is really able to double ads click, right? So enticing, people looking at the ads, they're like, wow, I wanted to buy this. And then, so when you are measuring the revenue impact in a regular A/B test, which is really we randomize on the user side, and you will see that, wow, the impact of this A/B test, this treatment is 100% lift, right? So it's doubling the revenue. But the real revenue impact is actually zero, right? Because you actually only has that $1,000 to spend. So what I'm depicting here is really thinking about this budget is really this tug of war between treatment and control. If treatment is spending more, that will make treatment look better than it really is and make control look worse than it is because you are sharing the same resource, the same budget. So how can we solve that problem? So you can certainly say, hey, why don't we actually start, again, similar approach as the cluster-based randomization. It's randomized based on campaign, right? So we have tons of different campaigns. Why don't we do that? Like this campaign, maybe half the campaign is showing treatment, is using treatment, half the campaign is using control. And the problem is really, first of all, again, a low power relative to the number of users. Number of campaigns is a lot less. And also, more importantly, the users or the members, in LinkedIn's example, they actually are able to see campaigns they are able to see different campaigns, right? So there is going to be overlapping with regarding the targeting of campaigns, no matter how hard you try to essentially isolate them. The same problem that we saw in the cluster-based randomization. And then you can say this is actually a very popular approach that I've heard like some other tech companies use as well, is they call this like alternating day randomization. Basically, day one, all users see treatment. Day two, all users and all campaigns are seeing control, et cetera, right? Again, low power is another problem. And on top of that, if we actually have campaigns that are under what we call lifetime pacing, which means, hey, I don't have a daily limit. I would really just say, hey, go ahead and spend this $1,000, and then we actually end up always using it. So it continues to be a biased result when advertisers or the campaigns actually have lifetime pacing. So the third solution is really the one that we actually, again, have in production, is what we call budget split. This is essentially a very simple idea, but it's very hard to implement it correctly. Basically, you take the budget, every campaign, you split the budget in half, right? So treatment half, control half. At the same time, you split the users who are receiving those campaigns. So again, 50-50, right? So then people in control can only utilize the control budget, and people in treatment can only utilize the treatment budget. Super high, much better high power and unbiased as well. So, but again, I'm not going to go into depth about it. But it's certainly, to get it done right, there's a lot of subtleties as well. So we talk a lot about, like, I give this one example in social network, the messaging case, and then we talk about the indirect connections in the ads budget utilization. I just wanted to show you all also that there is actually way more examples of this, right? Certainly thinking about phone calls, that A calls B on Skype, B picks up, right? So that is, again, it's a direct connection example. And then in the money marketplace examples, where if it is, say, a user is competing with another user over the same driver on Uber, right? So in this case, the driver is the shared resource. And then even on computers, you can think about a request is competing with another request over CPU on the same machine, right? So a lot of examples in these categories. So I'm gonna then quickly go over the other challenges that I may not go as depth. So the second challenge is about measuring long-term effect. And I actually wanted to start with a example, which is really a puzzling example, when I was at Bing, which is really many years ago. So at Bing, at the time, many years ago, that at least, like, we had this two key metrics, success metrics, right? One is you wanted people to search as many as possible. You wanted to be able to make money, right? So these are the two key metrics. So in one experiment that we ran, we ended up had a bug, right? So a ranking bug that is always doing, it was taking the results from the bottom of the page and then put it on top, basically, right? So what happened is that we saw that the number of searches went up in this experiment 10%, and revenue was up 30%. So the question is, hey, would you then launch that bug? right? The answer, of course, is like, no, it was a bug. It was not supposed to be. It's really showing that in experiment, sometimes we are not necessarily, what we saw in experiment is not necessarily the same in the longer term, what we would expect. In this case, as users learn, the results are not very good. They would abandon Bing as a search engine. They would stop clicking on the ads because they didn't find them as relevant. So really that this shorter term effect is not equal to long-term effect. It can be due to many reasons, and it's really impacting how we are measuring in our experiment. Obviously you can say, hey, the most common way, and again, I'm not gonna lie, like this is actually the most common way that adding ding that we measure long-term effect as well, is by just keep the experiment running for a long time. So you can see that it's certainly expensive, and in some cases may not be a good user experience either, right? So, but the idea is very simple, though, right? So you wanted to you launch your experiment, you keep it running, and you measure what the last time period as what you call as a long-term effect, and that is very different from the beginning of the effect, which is really the short-term effect. But it has a lot of challenges with this approach. I talk about practicality challenges, but also there is also like treatment effect dilution, because in some cases when you don't have user logging that is cookie based, you have cookie churn, you can have network effect that can be cascaded over the network over the longer time period. You have survivorship bias. You have the problem with interaction with other new features that is launching over this longer time period as well. So a lot of challenges, and then we have some alternatives, but again, like I don't think necessarily we have a perfect solution. So would love for this group to be able to help us figure out something that is more effective. So with that, I'm gonna actually pause a little bit to take a question before I go on to the third and the fourth challenges.
Okay, so perhaps we can have just one short questions in the interest of time. So one thing that we don't necessarily take into account very much in academia is the computational aspect of things. Now, I assume that you might be able to do more fancy things, for instance, in the interference setting, but more fancy things might be very, like, basically impossible to scale at the size of LinkedIn. So is this something that you take into account, like not just for the interference, but for like all of the challenges? Has it been something that has affected which solution you decided to implement?
Oh, that's a great question, and absolutely. Like if I'm thinking about, you know, even though that we have a lot more computation power than individuals, but then if you think about, we are dealing with the scale of hundreds of experiments, we're dealing with millions, tens of millions, hundreds of millions of user engagements at a time. And at the same time, we wanted to be able to have a higher turnaround, right? So we wanted to, you know, we're always pushing the limit. Like, you know, if you get the computation done in an hour, we want it to be in a minute. If you get it done in a minute, we want it to be real time. Like, so definitely always wanted to have a faster computation, and that any method that we are able to prove has a maybe just like slightly in terms of accuracy relative to what theoretically computational heavy method is, but then it's a lot faster. We always aim for, we will always go for that. Like another example is, you know, a lot of times in A/B tests we compute averages, but in some cases we actually have to use percentile. So if you use quantile and then thinking about how are you going to be able to estimate variance for the quantiles, it can be very expensive. You do like a bootstrap, or even just thinking about bag of little bootstraps. Like all these are actually expensive to do. And so we are able to actually have, again, use the right theory and then be able to do that like mathematically instead of computationally. And it turned out to be the biggest saving that we had on our computation. Like so always looking for that for sure.
Okay, thanks. I'll let you continue in the interest of time.
Thank you. So the third challenge is really sequential experimentation. I know this is not a new topic for this group, but just wanted to set a little context on how we use it in industry. So in industry, again, the way that we do is we ramp experiment as a ramping up process, right? So thinking about your goal is you have a treatment, your goal is to really ramp that treatment, assuming that's good, to 100% of the users. But you don't start there, right? Usually you start small percentage of the users who are in treatment, and then you're gradually ramping them up, right? And then the primary reason of this is really you wanted to be able to balance the risk, and you wanted to be able to measure, and then you wanted to be able to learn about users' reactions to those treatments. So, and then how can we then, the question is, how can we ramp up quickly, but also control risk at the same time, right? So you can think about formulating that in a sequential testing framework where you're essentially saying, hey, given all the information that I've accumulated in the past, and then what is my next step to do, right? Should I ramp up to the next ramp phase, or should I actually not? And if I were going to ramp to the next phase, what is sort of the percentage that I should be ramping to? What is my risk tolerance that this comes down to? So a super interesting problem. Again, I'll refer you to the paper that we had, but that's not just the only challenges that we have with regarding deciding the phase and then the pace that we're ramping. You can also say, hey, because we are ramping experiment in this time fashion, how can we then make sure that we are able to utilize the data from the 5% ramp for the 50% ramp, right? So today, when we are reporting what the results are from the experiment, we just take the 50% ramp, and then we essentially analyze in isolation versus utilizing the earlier ramps to reduce variance or some other things that we can do with it. And another very important question is, again, this area that is actually quite popular, and I want to say it's probably more more developed within, I think Facebook has done a lot more work in that space, is this adaptive experimentation, which is really that, hey, you have a big configuration space, right? Could be a color, shapes, and could be font size, could be, parameter of how many feed items you fetch, and how can you efficiently explore a very big configuration space and find the best configuration, right? It's like, again, it's this adaptive, this sequential experiment setting as well. So super important problems. I don't think there is a perfect solution in the industry at this time. So the fourth challenge is really the observational causal studies. In most of my talk today, we are very much focused on A/B test or randomized controlled experiment, but it doesn't always work, or it doesn't work for many practical reasons, all right? Sometimes it can be too expensive to have a control. For example, just imagine you establishing impact of running ads during Super Bowl. You have a control bucket. That is just like too expensive to have a control. And or you can have the desired unit cannot be properly randomized, or in some cases it's just unethical or illegal to do as well. So again, thinking about this hierarchy of evidence where you have correlation, observational causal, and then all the way to A/B test, is how are you able to solve the ones that you cannot A/B test with observational causal studies. And so the approach that we're doing really is, we know that this is obviously a very heavily researched field, is really to empower all data scientists at LinkedIn with the right automations. So what we did is we essentially implemented four so far, the most popular or the most applicable observational causal study methods, doubly robust BSTS, instrumental variables, panel data. And then each of them have their strengths and weaknesses, right? And then we are able to implement them all. Then for everyone who are doing observational causal studies, that they can do that in a rigorous way.
Yeah. Sorry, can you wrap up in the next 4 to 5 minutes?
Mm-hmm. Yeah.
Fantastic, thanks.
I'm not going to go through, there's some other challenges as well that I'm not going to go through, but certainly welcome you to read some of the papers that we have, and again, references and the books that we have as well. So I'm not going to take another question until the very end since I only have 4 minutes. So I'm going to go through some interesting applications that we have. I'm going to share 3 applications very quickly. So the first application is really in the field of fairness. So if you imagine that we're launching a product and there are 2 ways that our users can react to that, right? So one is that every user, every member loves it. So it increases their sessions all by 2. And all members can actually be impacted very unequally in this case, even though that the average impact are the same between those 2 experiments. So we wanted to be able to catch the case where members are actually impacted unequally. So we are able to utilize the Atkinson inequality index and then be able to measure that inequality in any metric in our experiments, really to help us identify any unintended consequences. As example is that this we have this particular feature that's launched that turns out that is able to help people who are having low social capital to gain a lot more than the ones with high social capital. So which really is bridging the network gap that we wanted to have. And then we do this for all experiments every round. And then the second example is where we are able to measure the strength of weak ties, basically utilizing hundreds of experiments variations that we have on the age recommendation as instruments, basically using Iavor approach that is able to help us measure causally that when we are able to increase members' network diversity, that they are up to 15% more mobile in the labor market that runs over a long period of time. And then the last application is actually really interesting, which there's tons of challenges, by the way, in this application. We haven't been able to solve a lot of them. So it's really how can we optimize based on heterogeneous treatment effects, right? So you can run experiment, obviously different segment of users are gonna react very differently to the treatment effect. And then here is an example that you wanted to give a marketing discount offer to users. So in the past, you would run 2 variants that you would identify, let's say, a country that maybe reacts the most favorably to your treatment. And then you launch the treatment only to this country. But now imagine that you expand in T to really being a lot of treatments, right? Lots of variations. You can change the subject, you can change the amounts, you can change other terms of the discount offer. And you also expand these segments to any arbitrary group of users or a very large cardinality, right? So the question is that, hey, can you go and find the pair of treatment and segment that works? And really being able to optimize using the heterogeneous treatment effects that we're able to observe in experiments. So with that, I'm actually gonna just spending 30 seconds talking about a lot of the materials that I covered today is actually in the book that we actually just recently published in this trustworthy online controlled experiments. It touched upon a lot of various different dimensions, many things that I did not cover, even the things that is very simple of how can we even run mobile A/B tests. There is a lot of subtleties and challenges in that space. So highly encourage you all to take a look at that. And also there's a lot of specific papers that are referenced in the talk as well. With that, I'm gonna stop there and hand it over to Iavor.
Fantastic. Thank you very much for this very interesting talk. It's super important for us to see what challenges you face in industry. All right, we're now switching over to the discussion. Yeah.
Yep. Okay. Let's do this. I'll try to be quick. All right. Sure. Okay. I'm assuming everybody can see that and get a thumbs up from my panelists.
Yeah.
Nice. Okay. Great. So first off, yeah, thank you for this awesome talk. It was great to hear some of these challenges. And thank you for the committee for organizing this and inviting me. So in the next probably 8 minutes, I'm going to try to be super fast. I'm going to try to do 3 things for you guys. The first thing is I'm going to just spend a little bit of time explaining why there are so many new challenges in online experimentation. The second one is I'm going to just quickly summarize all of the challenges that Jan mentioned into 4 distinct categories. And then the third one is I'm going to take one of those challenges and I'm going to just zoom in and try to give you a sense of where the theory is actually lacking, and give you some open problems that exist out there. Okay, so why do these challenges exist? Well, if you think about the theory of randomized experiments, it was really developed focusing on medical and agricultural examples, right? So there you had a small number of units that were being experimented on. You had a small number of outcomes, maybe 5, 20 outcomes. Each person was only in one experiment at a time, and typically there was no interference. Right now, when a technology company runs an experiment, they're running these, hundreds of thousands of millions of simultaneous experiments on billions of connected people, and they're measuring thousands and thousands of outcomes. To give you a sense of the scale, so Iavor gave you some numbers, but think about Google. Google has 2 billion monthly active users. That's their cohort that they're experimenting on, right? So they have a huge number of experimental units that they're running these experiments on. They also measure thousands of different outcomes. So it's not, you just have one primary outcomes. It's literally, these companies are tracking thousands of different metrics. And each unit is potentially in many different experiments at the same time. So there's a lot of interference happening potentially across experiments. There's interference happening over time. There's interference happening across units. So all of these, when you combine all of these new things, there's, these novel business applications are really presenting a ton of new challenges for statistical methodologies. So the way I like to think about the challenges, and these are basically what Iavor said, I've just kind of regrouped all of the challenges and then the novel applications that she briefly mentioned at the end into 4 categories. So the first one is looking beyond the average, right? So you have to measure heterogeneous treatment effects, but then, you have to go beyond just measuring them, and you actually have to design and optimize for them. Right? A lot of firms are trying to provide individualistic or personalized experiences, and you can do that through experimentation. So Susan Murphy last week, spoke a little bit about how her work is using bandits to do this. The second challenge is handling connected units, and Iavor spoke at length about this: network experiments, time series experiments, all of these things, all of these applications are at a scale that we haven't previously seen. Right? When Iavor talks about running a network experiment, she's running this on 6 million people, right? So you can imagine the size of that graph. So even, she was saying, clustering those graphs is incredibly hard. So a lot of the existing methodologies, they just do not scale to the types of problem people have to solve in industry. The third challenge, again, Iavor spoke about this at length, is estimating long-term impact from short-term data. First, how do you even get the length of the experiment right? And once you have it, how do you actually extrapolate from these short-term experiments? How do you get at the long-term effects? And then the third thing is experimentation velocity. Really, everybody wants to run experiments quickly because they want to get the right answer as quickly as possible. So this is where sequential testing, it's been around for a very long time, but these new applications are presenting a whole set of new challenges. And Iavor spoke a little bit about her framework for balancing speed and risk. So what I'm going to do in the last 5 minutes or 4 minutes even, I'm just going to zoom into this and just add a little bit more context to the thing that Iavor was talking about with what she called the phased release, which is essentially you're taking this product and you want to gradually release it over time from 0% of users having it to everybody having it. And this is typically the main application of A/B testing in industry, is this idea that you have something new and you want to release it in this phased and gradual release way where you're sort of able to control and balance risk, but you're also able to learn about, if it has any bugs or if there's any ways to improve it. So this is literally taking Iavor's paper. They kind of come up with this SQR framework, which basically starts off, and I'm telling you the most simple version of it. There's more complicated versions to it. But the first part is, you release it maybe to 5% of the population, and this is what's known as the risk mitigation phase. So here, if something goes wrong, it's okay because only a small subset of your users have seen this. Now, if this works out very nicely, then you might increase it to 50%, say, and that's where you have the most power to measure the effect, to get an accurate read of what is the impact of this innovation. Now, again, if you see a positive effect, then you might launch this. Okay, so now what I'm going to do is I'm going to just add a little bit more framework to this and a little bit more notation to it. So I'm going to give you a slightly different view of the first two phases. So, okay, so we start off with our group of people. These are smiley faces. For some of them, we're going to give them the new experience. For most of them, we're going to give them the control experience. So this is the phase one. Then in the second phase, now if this turns out to be a positive innovation, then I'm going to keep these people that have the new experience. They're going to stay in the new experience, but then I'm going to take a bunch of the people from the control and I'm also going to put them in the new experience. And then everyone else will stay in the control experience. This is the second phase. This is where you try to measure the effect. So if we add a little bit of notation to this, and I'm kind of flying through this, but I'm assuming everyone's pretty familiar with the potential outcomes notation. You know, W is my treatment. So here is WI is the treatment for individual I, and then 1 indicates that this is in phase 1. So here, you know, they either have B or they have A. And then we also observe two potential outcomes. Now, in the second phase, things get a little bit more complicated. And this was actually one of the questions that someone raised, which is, you know, these people are getting multiple treatments over time when you're doing this phase release. So what happens? Well, that's exactly what happens, right? So for the person that saw the new experience in phase 1, and they also see the new experience in phase 2, then they have, in some sense, received treatment twice, right? They have BB twice. And then the people who see the control and then the new, they see AB, and the people that see the control twice, they see AA. Okay, so this is just adding a little bit of notation to the framework that Ya presented a couple of minutes ago in her talk. And when you look at this and you start to think about it, you start to realize that these types of experiments they're running have a lot of dynamics that are not really accounted for by traditional A/B testing papers that people write. Okay, so when you open your eyes to that, you start to see, oh, I was just adding the potential outcomes. Of course, there's one potential outcome corresponding for every possible treatment path you could have taken. When you open your eyes to this, you start to see that there's actually a lot of interesting effects that you could start to measure, right? So the most obvious is just the average treatment effect at the first phase. But then in the second time step, you can measure the short-term effect by contrasting the people that were in the control in the first time step to the people that went into treatment to the people who have stayed in control, right? So that's the short-term effect. And this is in some sense very similar to this very first, hopefully you can see my mouse, very first effect here. You could also measure the learning, right? So you can measure how people who have received treatment twice, how they react differently from people who have received treatment only once. You can also measure the long-term effect by contrasting people that have received treatment twice versus people that have received control twice. Now, as I'm just kind of giving you this as a very fast introduction of how, when you start to think about the underlying framework and theory that underlines all of this A/B testing stuff that people do in the industry, it's actually very different from typical clinical trials that we're all used to thinking about. And it also raises a lot of questions, like how do you even design these types of phase releases, right? How did I pick that 5%? I just, you know, I picked it. But why? You know, why is each phase only one iteration in the example that I gave you? By iterations, I mean, you know, in the first phase, I only had 5%. Maybe I should have gone from 1 to 2% to 3%, right? Why did I pick that? How long should each iteration be? How long should I run this experiment for? What happens if the effect is negative, right? There's a ton of different questions. And the way people have answered these questions so far has been really to just use institutional knowledge to build up rules of thumb. You know, Apple, for example, recommends going 1, 2, 5, 10, 20, 50. Google, they allow phase releases, but they have no recommendations. Why is this important? Well, it's really, this question is actually really important to firms because if you release too quickly, you have a much higher chance of having mistakes go through and you have less time to learn. But if you release too slowly, you have a massive wasted opportunity and you really slow down the pace of innovation. And both of these things could potentially be costing a company millions of dollars. So what's my ask and what's next? Well, really, this is a problem. These problems can only be solved by working with the practitioner community, working with the statistics community hand in hand. Really, there needs to be a lot more sharing the challenges that are currently faced. So thank you, Ya, for doing that and telling us a little bit about some of the challenges you're facing. But practitioners really need to be open to collaborations with academics, and they really need to share some of the data so that we can start exchanging ideas. And then for the statistic community, my ask to you guys is really start to think about how to develop the mathematical formulations of these practical problems. Like right now, there is very little theory that actually describes what all of these tech companies are doing. And it's all pinned on these, you know, Fisher style classical experiments, which just do not hold in this setting. And then my final point is just be really thoughtful about application and practical considerations when developing new methodologies. I think when Iavor was answering Guillaume's question, she kind of mentioned, Guillaume's question was very much like, you know, people are coming up with these methods that just don't scale. And they're not very useful to practitioners if you can't scale them to extremely large data sets. So with that, thank you. It took me 10 minutes, so I'm okay. Yeah, thank you guys.
Fantastic. Thanks, Iavor, for this great discussion. Yeah, do you want to respond perhaps very quickly?
No, that was a great call out, I think, call to action in particular to this group. Thank you.
All right, fantastic. Then I think we're running out of time and we should slowly wrap up. So yeah, first of all, thank you so much, Iavor, for sharing your experience and how you're tackling the causal inference problem in industry. This was very interesting for us. Also, thanks, Iavor, for this very nice discussion. Next week, we'll have Paul Rosenbaum from the University of Pennsylvania. He will talk about replication and evidence factors in observational studies. We're very much looking forward to that talk. Yeah, then I hope to see you all next week and stay safe. Thanks for joining today.
Thank you.
See you guys.